Okay, in this video I'd like to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 3 and we're going to talk about compression work. The previous video was on the first law of thermodynamics. So very quickly a recap. The first law says the change in internal energy of a system is equal to the input heat, or the heat going out we'll say, plus the work done on or by the system. And we say that it's plus when it's done on, and we say the work done is negative when it's done by the system. And this of course is plus when it's in and it's minus when it's out, O-U-T. And that's the first law of thermodynamics. The change in internal energy is equal to Q plus W. Note of course it's very important that we define W in that way for it to be plus. Now, I may do a video yet on it, but I haven't done so far. You see, on the equipartition theorem. So where a system stores energy quadratically, in other words, well, quadratic C is a proportionality constant, but where it's quadratic, so it's to the power of 2. So we could be quadratic in velocity, could be quadratic in momentum, in position, you name it. If it does that, your system obeys the equipartition theorem. And if it does that, that means there is 1/2 kT kinetic energy per degree of freedom. So we say F is equal to the number of degrees of freedom, and we say that N is the number of particles. So what is a degree of freedom? Well, I'm not going to really go into much detail here, but a degree of freedom could be rotational, like that. It could be translational, or vibrational. Usually, and they're the 3 types of degrees of freedom we usually talk about. So in general, we can say that the internal energy of a system, it's not delta U, it's the actual internal energy of the system is equal to 1/2 N for the number of particles, F for the number of degrees of freedom per particle, and kT as the constant. And this is obviously in units of joules. So now it's time to talk about compression work. So we're saying work is being done on the system and it's being done in a compression manner. So let's say, for example, what we have is we have a system, here's my system, and we have some sort of a piston. And in it we have a gas. Alright, and I apply a force onto the piston like so. Now, if you think about it, if I apply a force like that, well then it is going to compress the gas and it is going to do work on the system. So where the force is in that direction, we say the force is positive. If, however, for some reason the piston was going, as you look, to the right, well then this time the gas would be doing work on the outside, so work would be negative. And why would the piston be doing work on the outside? Well, the pressure on the inside might be greater than the pressure on the outside, for example, and a pressure differential will cause such work to be done, for example. Now, let's talk about the work done if the piston is compressing the gas, in this case to the left. Well, we know that the work done has to be positive because work is being done on the gas, and we defined that to be positive work. So think about your regular mechanics. We know that work done, if it's a vector, is equal to, it's actually not a vector, is it a vector? Yes, it is a vector. No, what am I saying? Work is not a vector. That's silly. Sorry, so the work done is equal to the dot product of the force and the position vector. Okay, so in one dimension it's f dx. Okay, if we're talking about, so let's say this is, there's I hat there. Yeah, so it's f dx, or f dot dx. Okay, so we're going to apply a force in the x direction, like that. There's the force. But we're applying force on the unit of area. The unit of area, of course, is the piston. So we know that pressure is equal to force per unit area. That means force is equal to pressure times area. So another way of another expression for the force we are applying on the piston is the pressure times the area. Okay, the pressure on the piston times the area of the piston. So that means that the work being done is F dx is equal to P A dx. Now think about A dx. Well, let's say here's my area and here's my volume. So this is A, this is dx. Well, an area times a thickness is a volume. So that means that A dx is a volume. So I'm going to go, we have P A dx is equal to P dV, or P delta V, the change in volume. Alright? So the work done is equal to the pressure multiplied by the change in volume. Now, this is where we just need to do a small bit of thinking. We have, in this particular case, we have defined the work as being positive because the work is being done on the system. However, what way is the volume going? Well, let's say this is volume initial, and let's say the piston goes to here, there's volume final. Well, delta V in this case is negative. So where the change in volume is negative, the work must be positive. That means we must add in a negative sign here. Alright? So we can now say that the work done is equal to minus P dot delta V. Now this is quasi-static. And this means, let's say for example, it means that it's done in small infinitesimal steps. So let's say there's this, we're compressing it, we don't do this, that it wouldn't be infinitesimal. So we would do it in small little steps, and in between each step we would allow our system to come into thermal equilibrium, and that's what quasi-static means. So work done in quasi-static nature is negative P dot dV. So let's think about let's think about this then. If we look at a pressure volume graph, here's our volume, there's our pressure, there's VI, VF. So in this case we are expanding the gas. So what's the area of this particular piece of this particular shape? Well, the area A is equal to the pressure times VF minus VI is equal to P delta V. We said a moment ago that the work done is negative P dV. So it's looking like the area on a pressure volume graph is equal to the work done, or negative that is the work done. So what if we have the following? Let's say we have something that looks like this instead. It's a P here and V. Like I said, it's quasi-static, so we can break it up into these infinitesimal changes in volume. And this should ring a bell to you because it looks like a Riemann sum. Riemann sums make integrals. So what we can say here is the area is equal to the integral of P as a function of the volume dV. P as a function of the volume dV going from V initial to V final. All right, and that's how we are going to redefine our expression for compression work. So I'm going to say work done in a compression nature is equal to minus the integral of P as a function of volume dV going from V initial to V final. That's the compression work. And by the way, this is quasi-static. Quasi-static, I explained what that is. We're going in small infinitesimal jumps. So if I want to compress a box that says this way and I do it like that, that is not an infinitesimal jump. You must do it in small infinitesimal steps so that it is in thermal equilibrium throughout. Next, what else do I want to say about this? Oh yes, now in order to get pressure as a function of volume, you need to talk about the ideal gas law, believe it or not. The ideal gas law, PV is equal to NKT. I like to think about this, I know it's Boltzmann's constant, but I like to think about it as the molecular gas constant. Because if we're talking about the number of molecules here, so it's the molecular gas constant. PV is equal to nRT, then I would think about the molar gas constant. So PV is equal to nRT. I like to think about this here or as the molar gas constant because we're talking about the number of moles. That's just the way I like to think about it. So anyway, look, if we rearrange the ideal gas law, we have P is equal to NKT over V. Therefore P, a function of V, is equal to NKT over V. Alright? So what does that mean? Well, let's put, it means our work done is equal to nkt with the minus sign, Vf, Vi, then we have dV over V for quasi-static compression work. And let's go ahead and do the integral. Well, this of course is going to give us a natural logarithm. So W is equal to minus nkt, the natural logarithm of Vf, minus the natural logarithm of Vi. If we bring the minus up here, we're going to have a minus 1. And if we look here, the two natural logarithms being subtracted is the same as the two natural logarithms being divided. So it's the natural logarithm of Vf over Vi, like that. However, because there's a minus 1, we're now able to swap it, and it becomes Vi over Vf. And we can say that compression work is the natural logarithm, is nkt times the natural logarithm of Vi divided by Vf. And that gets the compression work in terms of the volume. All right. So I'm just trying to think now, is there anything else I want to do? No, I think that's all I want to show you in this regard. Okay, so thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're a good root, you might also click on an ad. Thank you.